Hey guys, welcome to another session on matrices. Now, today I was thinking we could do a bit of Cramer's rule. And when I say a bit of Cramer's rule, I'm not exactly speaking about the application. I want to get into how Cramer's rule came to be, or its proof, if you want to think of it like that. So some students tend to be mind blown when it comes to Cramer's rule because it looks so cumbersome, so tedious, so like really compacted with letters and variables. But I want to simplify that for you guys a bit. Now, the first thing you need to understand with Cramer's rule is that you need to know what's the purpose of Cramer's rule. Now, Cramer's rule is very useful when trying to solve equations of this format. You have over here, we have a system of equations. You can call it two simultaneous equations. So for example, this first equation here, we can call it equation 1. The second one here, we can call it equation 2. And if we have two equations, essentially what you want to do are solve for values of x and y if all of the letters A and B were known values, such as 2, 3, they were just regular numbers, right? So how can we go about doing this? Now, as you guys can recall, when you're using matrices to solve simultaneous equations, you can set up your matrix in this format where you would write the coefficients of each variable of x and you will write them down in brackets. This is supposed to be x, man. Let me change that color. All right. So usually what you would do is write down all of your coefficients in a nice matrix format here. And the reason I'm showing you guys this is so that you can understand clearly exactly how they got these notations or these subscript values of 11, 12, 21, and 22. Once again, those elements belong to a certain position, a certain location in your matrix. For example, this first A11 element, it belongs to row 1 and column 1. Hence its name is A sub 1, 1, row 1, column 1. Let's do a second one for recap. A sub 2, 2 belongs to row 2 as well as column 2. Hence its name A sub 2, 2 or A sub 22. So these values are not so much arbitrary as they are based on their location within a particular matrix system. So make sure when you're thinking of trying to find the proof for Cramer's rule as to how they generated the formula for x and y, you keep that in mind. Okay. So now what we're going to do here is we are just simply going to solve these equations simultaneously, okay? Now, the first thing you do when you're solving equations simultaneously, you don't have a lot to work with, you can apply the elimination method. And applying that elimination method, what we want to do is observe that first equation, and we are going to multiply our equation 1 across by, let's just say, A21, right? So we're going to multiply it by the coefficient of the second equation. In doing that, we will end up getting, we will get A21, A11, x plus A21, A12y is equal to A21, B1. Be very careful when you are doing this multiplication. It's so easy to write number wrong or letter wrong, just take your time. All right, and next what we want to do is we would like to create our fourth equation, and we're going to do that by multiplying our second equation now by the coefficient of the x variable, which is A11. So multiplying equation 2 by A11 will give us A11, A21x plus A11, A22y is equal to A11 and B2. Yeah, I don't think I see any errors there, guys. So we're good to go. Now, we have generated two equations, equations 3 and equations 4, two new equations, which if you observe them, they do have similar coefficients of x now. We have A2111 and we have A1121. So by the elimination method, we can successfully subtract these two equations, and let's see what's going to happen if we subtract these two equations. So we're going ahead here using that elimination method. All right. So we're going to say equation 4 subtract equation 3. What is that going to give us? Well, let's see. If we subtract equation 4 minus this one, obviously the first two terms are going to cancel. Then we'll end up getting A11, A22y, which is this term here, subtract this one, which is A21, A12y. Now that takes care of the left-hand side of these two terms here and here. Now we want to deal with the right-hand side. You have to remember which equation you were subtracting from which one. We took equation 4 first, and then we subtracted equation 3. Make sure you check that your terms are correct. 11, 22, 21, 12, 11, 2, and 21, 1. So that's check. We're good to go. Now, what you will observe is that on the left-hand side, we have like terms. Remember, you need to see past all of those variables and numbers in that equation. You really, really do. You have to be very vigilant. Essentially, we have really just one unknown variable, which is y. A sub 11, A sub 22, all of those A subs and those B subs, they're just really going to be values at the end of the day. The only true unknowns here are essentially y and x. All right, guys, so what we want to do is we want to factorize. We want to factor out that y, and we want to write those remnants in brackets. So you'll have 22 minus A21 and A12. And on the right-hand side, we have 11b2 minus A21b1. And then finally, to make y the subject of the formula, people, it will just be equal to A11b2 minus A21b1 divided by, we're going to take that bracket, carry it across, divide both sides by that bracket, taking our times, and we end up getting something like this. Now, it looks difficult at first, and it doesn't exactly look 100% like the Cramers rule, but if you remember, when you were doing determinants, let me just recall something here on the side. Okay, guys, let's recall. If you have A11, first row, second column, second row, first column, second row, second column. If you recall this, if we had to find the determinant of this matrix, if this matrix was called A, the determinant of A would be equal to you have to multiply by the leading diagonal, which gives us A11, A22, subtract the product of the other diagonal, which gives us A12, A21. Now, if you observe this, you'll notice that it's kind of in the same format of the numerator and the denominator down here. So it seems like the numerator and denominator may actually be determinant values. So what Cramer's rule lies heavily upon is the fact that if you could figure out the determinant that these values came from, we can actually use that as a model to work out our value for y. So let's think a little bit backwards. Let's take it one step back. Let's just say that we're trying to figure out what were the determinants that created these numerators and denominators. Let's set up a determinant both on the numerator and denominator. Now, usually our leading diagonal starts from this value here, the first one. So observing this product, A11 times B2, and knowing that A11 is located in that first row, first column, I will write in my values A sub 1, and B2 as follows. So that if we were to find the determinant of this matrix, we would get that first term. Now, subtract is understood because when you're finding the determinant, you subtract the products of the diagonals. And then secondly, we have the product of these two, A sub 22 and B1. Now, we do know that where there's 2, 1 lie, that's the second row but first column. So that means A 2, 1 should lie here, second row, first column, and not up here. And then it must mean that B1 should belong to the upper portion of that determinant there. So uniquely thinking a bit in the reverse sense, you can carefully take your time and you can place those 4 values into the respective positions such that the determinant of this numerator gives us back what we had just before. And you apply that process once again to the determinant in the denominator. We would like to look at this term here, A11, A22. Let's think about it. A11 and A22 would belong to those 2 respective positions. And then the second diagonal, A21, let me see, A second row, first column, and first row, second column. So yeah, that's correct. And then we end up getting Cramer's rule for finding the value of y in a system of equations using the determinant method, right? So essentially, if we had gotten values for A and B and so on, we could apply Cramer's rule successfully to find it. And this rule also applies for the x value. If you were to perform the elimination method, you would also similarly be able to solve for x, where x looks like this. I'll just show you guys on screen. You can do the proof on your own, but x tends to look like this: B1, B2, and then you are left with a first row, second column, and a second row, second column over the determinant of 11, 12, 21, and 22. Okay, guys, so these are the 2 main formulas. A lot of students, they tend to memorize it and mix it up in exams. So if you do, this is how you can essentially work it out on your own to make sure that your formula is correct. Now I want to show you guys the, of course I can show you guys a shortcut, by the way. I just want you guys to notice something. Let me do a question and I'll show you a secret. Well, what students typically do to remember Cramer's rule. All right, so let's do a question. Let's do an example. You know, examples are so wonderful. They just clarify everything. So let's just say we had a system of equations 2x plus y equals 3, and we had 3x minus 2y is equal to 1. This is our equation 1, and this is our equation 2. Breathe. Take a deep breath. Sigh of relief. We have numbers, people. Yay! Numbers! Oh, wonderful. And of course, if you wanted to set this up into a matrix form, you could have done that, where you have 2, 3, 1, -2, and so on, right? You could have had your x and your y, and then your 3 and your 1, and you guys can go ahead and solve using another matrix method. But we're looking at Cramer's rule here today, using our determinants to solve for values of x and y. So using Cramer's rule, we learned that the x values, all right, x values works out to be equal to, and the formula goes like this. All right, so on the bottom, we're going to have a 11, 12, 21, 22. And on the top, we're going to have B1, B2, and 12 and 22. Now, I know a lot of you are worried. You're worried because you're wondering, how are you going to remember this? Well, this is a little trick I want to show you guys. Formulas are they're just formulas. They're complex if you don't understand the concept. But here's the concept. You see that determinant on the bottom with all of those a sub numbers, and you know what they are? They're just the determinant of the matrix that exists in the equation, people. Let's look at it. They're really the values in that order. We have 2 as the first value. We have 1 as the coefficient of y in the first equation. Looking at equation 2, we have 3 as the coefficient of x, and we have -2 as our coefficient of y in our equation 2. So essentially, when you're using Cramer's rule to solve for values of x, you are really writing the determinant of the given matrix in the question. Very simple. So no need to memorize any formula, people. And the numerator is also simple. You can think of it like this. Okay, so if I want to find my x values, I am going to set my first column to the values on the right-hand side of both equations. So I'm going to set my first values to 3 and 1, which are these two values here. And then I'm going to continue writing out the rest of my given matrix in the question. The rest of the given matrix was 1 and -2. So we will write 1 here, and we will write -2. As easy as that. It's just a matter of replacing whatever you want to solve. You replace that column with the values on the right-hand side of your equation, and you solve from here. You know how to find the determinant of a 2 by 2 matrix. For your numerator, this will simply be 3 multiplied by -2, subtract 1 by 1. On your denominator, you will get 2 multiplied by -2, subtract 1 multiplied by 3, or 3 multiplied by 1. The order in which you do this is not essentially 100% important because multiplication is commutative. All right, guys, and this answer works out to be equal to 1. All right, so you guys can plug these in your calculator and just verify with me. Similarly, let's check what happens for y. So what I'm not going to do is I'm not going to write that huge equation, right? What I'm actually going to write in all of its simplicity, guys, is that shortcut or trick that I'm showing you guys. So in the denominator, you will always write your matrix as it is given on your left-hand side using your coefficients of x and y's. So your matrix is simply 2, 3, 1, -2. And on your numerator, if you're finding the y values, then you want to replace your column 2 with your y values of, sorry, not your y values. What am I saying, man? You want to replace your column 2 with those values on your right-hand side that the question has given us, 3 and 1. You want to replace it on your right-hand side. So if you're finding x, you write it on your left. If you're finding y, you write it on your right-hand side. And you continue writing out the rest of your given matrix. It was 2 and 3 here. And you just go ahead and work, you find your determinants, and I'll just tell you guys the answer for this works out to be 1. Therefore, make sure you state your both values. X worked out to be 1 and y worked out to be 1. So it's actually more straightforward than you think. It's not so much to remember the entire thing, but rather what is being replaced. Okay, guys, so if you would like to see a full tutorial showing a lot of examples of these types of questions, just make sure you comment below and make sure to like, and I will be sure to do a full tutorial session, probably about 5 or 6 questions, showing you guys how to find the values of x and y, how to solve a system of equations, using Cramers rule for a basic 2x2 matrix, if you want to think of it like that, or a system of equations which involves 2 unknown values. Okay, guys, so it was good to be with you, and I wish you guys all the best. And please look forward to seeing my video on Cramers rule for 3x3 matrices. It's coming up next. Okay, take care. Bye-bye.